All right, let's take a look at one of the biggest theorem in this class, section 10.8, Stoke theorem. This is just a record the definition. Curl F is the cross product of the vector field F and the partial derivative vector. Partial X, partial Y, partial Z. And then the vector field F have three components, X, PQR. Okay, this curl F is just describe how the vector field rotate. Rotate along an axis. So the curve C enclose the surface S. Well, if the curve C travel counterclockwise, right, and the unit normal vector pointing upward, so go up. Then we have a positive orientation. This way it look like. The best way to remember is to use your right hand side. Use your right hand. Put a note here. So what you want to do is that if you curl a finger counterclockwise, then your thumb point up. Your thumb is the normal vector. Okay, what is the Stoke theorem here? Let me say let S be an oriented piecewise smooth surface. Piecewise smooth surface that is bounded by a symbol closed piecewise smooth boundary curve C. What positive orientation? Let F be a vector field host component have continuous. Partial derivative on an open region in R3 that contain S. Then that is true. And we're gonna have this one. Well, integral C f dot dr. It's the line integral. That is the, well, you can know as the circulation is equal to double integral S curl F dot ds. Yeah, this is a very powerful theorem. What it say here is that circulation in R3 is the flux of current through the surface S. So here come something that related to what we have learned before. Right? If you can tell right here, if S is a flat surface on R2, what the unit normal vector K then what we have here is the circulation f dot dr is surface integral curl f dot ds. Well, the unit normal vector is k, so this is gonna be a double integral curl f dot k, because you're gonna dot the unit normal vector and dA, so it's gonna be double integral over some region D, which we know that, well, we did the curl f dot k and it is just double integral over the region D, qx minus py dA. And so as you can see, Green theorem is just a special case of the Stoke theorem. It is very important that you know what it means, right? It's just circulation in R3, and it is the same as flux of the curl F through the surface S enclosed by the curve C in R3. The vector field F and the surface S negative y x minus 2 S is the cone oriented downward. X squared plus y squared square root Make it a little bit more difficult here. For 0 less than equal z less than equal 4. Yeah. Oriented downward, so yeah, reason why I want to do oriented downward, because I want you to be careful with the negative. So here come step 1. Just 2 steps here, huh? Compute. Well, you want to compute the left side, circulation in R3. There's circulation in R3 here. It should be too difficult to compute this thing, right? You just have to sketch out the curve C and parameterize the curve C. Okay, so the cone Z go from 0 to 4, so we don't have to deal with the negative side. So here come the curve C and it travel clockwise. Now, as you know, there's the curve C right here. And because you cannot draw the curve C on everywhere on the surface, S is on the top. There's the curve C. F dot R prime T dt. Okay, so now let's just parameterize this thing here. Okay, I'm gonna parameterize the curve C. Now, according to this one, how do you parameterize the curve C? It was x equal to, y equal to, and z equal to. Next step is where t go from, well, there's the full circle, 0 to pi. 0 to 2 pi. F, right? Negative y, so negative 4 sine t. For cosine t, minus 2, right? Dot. For cosine t, 4 sine t, 4 dt. C traverse clockwise, so if it traverse clockwise, then you got to do the negative C. Oh man, that one, let's be a little careful. So negative C is gonna traverse the counterclockwise. So you put a negative here. That's the negative right here. Negative. Yeah, this small detail here. Okay. Negative 16 Oh, yeah, this is all t. It is not all prime t. I say, what the heck? So all prime is the derivative of cosine negative side of negative 4 sine t, 4 cosine t and 0. 10 sine square t plus 10 cosine square t plus 0 dt. Oh, so what we have is the negative of integral 0 to 2 pi 10 dt, right? So that's going to be negative 10 times 2 pi minus 32 pi. We know f is the minus y x minus 2, right? And then here's going to be a parameterized c. So you have to use the parameterized c. And it would be a minus 4 sine t 4 cosine t minus 2. So that's where I get the f, right? And then the RT is, oh yes, you do have the homework because you have this on the final exam. It's a requirement. Because if I don't put this on the exam and when the university asks you, have you taken learning material on Stoke theorem and the divergent theorem, you say no, they're gonna disqualify this class. Yeah, so you have to retake it again at the university level. For cosine t, for sine t, 4. So all prime t, negative 4 sine t 4 cosine t 0. Do a step 2. We're gonna compute flux of current F through S. Same thing here. It's the right hand side. X equal, Y equal, Z equal. Just a cone. The best way to parameterize this one is you can just parameterize it using rectangular coordinate. Save your life. X equal X, Y equal Y, Z equal to fxy, and that would be square root of x squared plus y squared. So if we parameterize S this way, right, then we're gonna have a region D. Draw a circle here. Don't bother to write out what is, where does x go from and where does y go from, right? No. Okay, if you look at here, root of x squared plus y squared, you can use polar coordinate later. Okay, we have to do more though. Reason why it's more because it's curl f dot ds. So last time we already did it, so use it. Remember I told you guys last time. And you don't have to overkill yourself. Yeah, this one right here. Let's see. If you do this, then all x cross all y. This is the normal factor. Let's use it. All x cross all y minus fx minus fy 1. So this would be a minus derivative with respect to x is going to be a x over root x square plus y square minus y over root x square plus y square 1. So however, if you notice that the normal factor is pointing downward, so you need to negate this thing here. I, J, K. And then the vector field F. This is the surface, the vector field. Oh, negative yx, negative 2. Okay. Let's see. So 0 and 0. So it's going to be 0. Oh, 0, 0. So it's going to be 0. 1. 1 minus 1. So it's going to be 2. Oh, how nice. And now curl F dot the normal factor. Oh man, you know, you can just put the negative in front of the integral if you want to, because with the notation here, it can be I put this thing here. Okay, 0, 0, and but then you have a negative in front, so you're gonna get a negative 2. Right? Parameterize S. Okay. So there's the double integral over the region D. Minus 2 dA. Minus 2 double integral over the region D dA. You don't have to do anything here, because you can just make an argument like this one, this area of circular disc radius 4 circular disc radius 4. What radius 4? What arc 4? Well, we know how to compute this thing here without using any. So it's the pi r square. It's going to be a term pi 4 square. Pi r square. Minus 32 pi.